Hello, everyone. My name is Alexi Charalambides. I'm a PhD student at the University of Maryland, and my talk is entitled An All-Elastomer In-Plane MEMS Capacitive Tactile Sensor for Normal Force Detection. So the motivation behind this work is to create a sensitive robotic fingertip. With this fingertip, you could grasp delicate objects, you can interact with humans safely, and in general, you can improve overall manipulation, exploration, response of robots. However, there are significant difficulties in emulating the sensitivity of a human fingertip. This includes the fingertip has high spatial resolution, a large force range and sensitivity. Fingertips are soft and conformable and very responsive. So there's been significant work in tactile sensors in the recent years. Most sensors are typically, they have one property but perhaps lack another. For example, they may be flexible and have a high spatial density but lack force sensitivity. Others may have ultra-high sensitivity but low force range. Some are extremely sensitive but have a large spatial area, etc. So an all-inclusive tactile sensor remains elusive. So ideally, a tactile sensor for fingertip emulation would have these properties. So it would have a sensing resolution of 1 millinewton, a sensing range from 0 to 1 newtons, be able to sense forces in 3 axes from normal to shear, among others, including a thin thickness of less than 500 microns, 1 sensor per millimeter squared, and soft and conformable. So my work is focused on capacitive sensing. The approach we used is capacitive sensing. And we chose this over resistive sensing since it's been shown to have, suffer from hysteresis. The fabrication process is a MEMS-based fabrication process, which in itself has several advantages. With MEMS fabrication, you can have high sensor density, you can fabricate small electrode gaps, which I'll emphasize later in the talk. You can create simple in-plane designs, you can integrate non-planar electrodes, you can use compliant materials, and you can even integrate with CMOS fabrication. Okay, so onto the microfabrication. It's done on a bare silicon wafer. First, it's masked and patterned, and a deep reactive ion etch is conducted down to 100 microns, as you see on the right. What you're looking at are pairs of electrodes, and these are in plane to the silicon wafer. Next, it's refilled with a conductive polymer. This polymer, we chose silver nanopowder and PDMS. In this case, the silver nanopowder had particle size of 80 to 100 nanometers. It was at 72 weight percent. It's refilled and planarized, and then a layer of PDMS is spin-coated. Next, the mold is removed in 2 steps. The backside is first diced to increase surface area, and then it is placed in xenon difluoride to fully etch the mold. So the surface area is important just to decrease the etch time in the xenon difluoride, but even after that step, it can take upwards of 16 hours to etch for an area this large. Lastly, the backside is again spin-coated to encapsulate the device, and the overall thickness is 400 microns, which is within our target, and it remains very flexible. So the latest work since submission of the paper involves the coating of Teflon after the mold is created. This is to utilize the anti-stick properties of Teflon between the PDMS and the silicon mold. Then something called a soft planarization is done, which is just planarizing the conductive polymer during the uncured state. It's cured, and then the PDMS is spin-coated, and this device can simply be peeled off. So no need to etch the mold or get rid of it. You can just reuse the mold, and it greatly reduces fabrication time. And then, as usual, the backside is encapsulated in PDMS. These are some SEM images taken of devices made using the Teflon peel method. On the left-hand side, you can see there are 4 capacitor arrays. These are oriented in a 2D spatial array. And in this case, we have non-planar electrodes. On the right-hand side, you can see just a series of conductive structures we refer to as resolution marks. And these marks kind of indicate how well the material was lifted off from the mold. And it can create features down to 10 microns with an aspect ratio of 10 to 1, meaning it's 100 microns tall, but at a much lower yield than a larger structure, say, of 30 microns. Also, since the paper, there has been some characterization done of the silver micropowder and PDMS. Qualitatively, it remains elastic, which is just simply demonstrated in these photos. It has a low resistivity. It's very repeatable in fabrication and produces stable measurements. It's typically also less expensive than nanopowder, which is what we used in the paper. In this case, we're using a 2 to 3.5 micron particle size, which is about half as expensive as the nanometer silver. On the bottom left, you can see the function, resistivity as a function of silver weight percent, and we observed a percolation threshold between 55 and 60 weight percent. On the bottom right-hand side, you can just see a series of samples from different batches demonstrating the repeatable nature. For the test setup, the method was very simple. It's to apply a force and measure the change in capacitance. In this case, a cantilever beam was fabricated using, modeled in Pro-E and then laser cut out of Delrin. And the principle is simple. We apply a mass at the center of the beam, and then half of the weight is transferred to the probe tip. Capacitance is then measured using an analog devices evaluation board, but the problem with this test setup that we found is that being manual in nature, it is prone to inducing large deviations in our measurements, which could be due to how you place the weight, how you place the probe tip, etc. An analytical solid mechanics model was developed, and the premise is, again, pretty simple in nature. A normal force causes the material to flatten and separate. That causes a separation of the electrodes through Poisson's effect. The change in capacitance has been shown to be a linear function of normal strain, EZ, thanks to work done by Cohen in 2012, as shown in equation 1. In equation 1, we have the vacuum permittivity and the dielectric constant and the normal strain that I just mentioned. And L, D, and G naught are all the initial geometric parameters of the electrode. Earlier I mentioned the importance of gap size, which is G naught. So G naught, changing capacitance is inversely proportional to G naught. So it's important that G naught is as small as possible, which is it can be tailored thanks to our fabrication process and directly controlled. We assume a linear elastic material model, which should be valid for low strains, as you see in equation 2. And equation 3 is just sensor sensitivity, which we define as the change in capacitance as a function of force. Based on our design, we expect a decrease in capacitance as force is applied. These are the results from the planar electrodes. On the right-hand side, you can see y-axis is change in capacitance as a function of force. And on the left-hand side is a blow-up of the low force region. And the lines are the analytical models that were developed. These are for 3 different sensors, 3 different gaps of 10, 50, and 100 microns. And as you'd expect, we found about an order of magnitude higher sensitivity in the 10 micron gap over the 100 micron. In addition, it's important to note that at higher forces, there is a decrease in sensitivity, which could be due to the material reaching a saturated state in which it can compress no further. A few additional tests were also done in the time domain. On the left-hand side, there's a plot of capacitance as a function of time, again for those 3 gaps. And as expected, we found a largest change in capacitance for the 10 micron gap. And it's interesting to note that the response times of the sensor was less than 0.1 seconds, which was actually probably a limitation of the analog digital the board that we used, which has a sampling rate of 90 hertz. On the right-hand side, we have a similar plot, also in the time domain, but for a single capacitor of 80 microns, and various forces are applied. So as the force increases, the change in capacitance also increases. It's interesting to note that only after 1 cycle for the highest load case, there is noticeable hysteresis during offloading. Lastly, a non-planar electrode was fabricated and tested. and it was found to have about an order of magnitude higher sensitivity than a corresponding planar electrode. So the premise was, although we couldn't necessarily analytically model it, we assumed that a higher surface area in between the electrodes would net a higher sensitivity. So in summary, the contributions of this work are the first in-plane conductive elastomeric capacitors. It utilized a very simple fabrication process. In this process, we were able to create non-planar electrodes, which showed an order of magnitude improvement in sensitivity. And in the future, we'd like to do a spatial resolution characterization of the structure I showed you earlier. Also incorporate shear sensing structures using a multi-mask process so that in our mold we can create a mold with multiple depths. And lastly, in the long term, fabricate onboard CMOS integrated with our sensor. This work was funded by NASA, and I'd like to thank Mr. Timothy Miller at NASA Goddard for helping us with our deep reactive ion etches.